Okay, so welcome to the data science seminar today. So I'm very happy to introduce Pratik Chaudhari. So Pratik got his PhD in 2018 from UCLA. And since then, he was a postdoctoral associate at Caltech and also a senior applied scientist at Amazon Web Services. So he's currently an assistant professor in electrical and systems engineering and computer and information science at the University of Pennsylvania. He just received the NSF Career Award and the Intel Rising Star Faculty Award this year. So his research interests are in deep learning, robotics, and computer vision. And so I'm very happy to have him here today to talk about, he's going to tell us, does data induce capacity in deep learning? So thank you.
Thank you. I hope everyone can hear me fine. Thank you for the invitation. I was here a few years ago, really enjoyed that visit. I've also been enjoying this one so far. So nice to meet some folks again and some new ones. Today, I will tell you about some recent results on understanding generalization in deep learning. And somewhat to lay the context, I want to introduce to you two specific questions. So we know that neural networks work well. I think that is, and there is a lot of evidence for it right now. There is two key paradoxes in what we think of them and what they actually do. The first one is why is it that we can train these models efficiently? These are very large models. They have lots and lots of parameters, millions of parameters. You will also typically train them on millions of images or millions of data points. And the function that you're minimizing, the objective, is not convex either. So by all measures, these are very, very hard optimization problems. And you really should not be able to train them at all. But you can. You can do it on your laptop. You can do it for even very large models. So clearly something has to be easy in what these functions are, otherwise you wouldn't be able to train them in the first place. So a lot of my PhD work was on understanding this question. What is it that is easy in this energy landscapes? And the rough thesis is that, look, they are not convex, but they are not that bad. They're pretty close to convex. The thing that I'll talk about today is the second aspect of this paradox, which is in high school, people told you that if I give you 10 data points, you should not fit a polynomial of degree 15 to these 10 data points. In deep learning, we love doing this. In fact, the larger the model that you fit, the better the results you get. So somehow, this very basic accepted statistical wisdom does not seem to apply. So what we would like to ask it is, again, like, what is it inside the problem that allows you to overfit with abandon and yet not get hurt by it? Okay. To set the context, I'll tell you about two specific peculiarities in deep learning. These are some from my work. There are many, many other weird stuff that you see in the world of deep learning. I'll talk about this one. So a few years ago, we noticed that when you train a typical neural network, it tends to converge in regions that are locally very flat in the energy landscape. And so this is a picture of the eigenvalues of the Hessian. The Hessian is a matrix that measures the curvature of the loss function. So when this matrix has lots of zero eigenvalues, that tells you that locally there are many directions in which the loss doesn't change much. There is a few positive eigenvalues where the loss increases locally, and there's also a few negative eigenvalues where the loss decreases. So typically at the end of training, you find regions that are not really local minima. This is the saddle point with both positive and negative eigenvalues. But the most interesting aspect of this picture is that it is a very wide region locally. Many, many directions are flat. Some directions are positive, some are negative. And this trend persists across different architectures, different data sets, different input modalities, etc. You again and again find such regions. Now, what is also true is that if you train these models and you arrive at regions that do not have these many almost zero eigenvalues, then they tend to have a worse validation error. So when you converge to nice spaces, you converge to these wide regions. If you converge to regions that are not wide, then you also do a little worse on new data. So this was an empirical finding many years ago. And the way we went about this question is we said, look, when training works well, it reaches regions like this. So why don't we modify the objectives to bias training towards such regions at all, in the first place? And so we were constructing objectives of this kind. So f of w is the training loss in this case, the one that you would typically use for optimizing the network. We were playing with objectives of this kind. So G sub gamma is a Gaussian kernel in the weight space that is convolving this function e raised to negative f. And what this convolution does is that it destroys parts of the energy landscape that are relatively narrow or not very wide, and it keeps the stuff that is wide. So this is how it biases your optimization to such regions by not letting it go to the non-wide regions. And we had a lot of success with these kinds of objectives. Algorithms to train neural networks with these objectives are still some of the fastest ones I know, about 2 to 4 times faster than stochastic gradient descent. And they also obtain good generalization error. So that is nice. But such regions are very peculiar in the energy landscape. So you can do some analysis using tools in statistical physics to convince yourself that not all regions in the energy landscape can be like this. In fact, these are exponentially rare regions in the size of the problem. So finding such regions is incredibly hard to begin with, and that is why biasing these objectives works so much better than SGD. It is also surprised why SGD finds such regions in the first place. Okay, so first peculiarity is you are traveling this room is very large, but then you seem to find these very, very tiny parts of the room, very rare stuff inside the energy landscape that also works better somehow. The second one is a little more abstract. So what I was interested in doing was, we know that we are solving a non-convex optimization problem. In a non-convex world, it doesn't make very much sense to say, I converge to a critical point very quickly. Well, there are many critical points. Which one do you converge to? It's a lot, you can understand this conundrum slightly differently and say, I'm not interested in understanding how fast I converge. I'm interested only in understanding what are the typical kinds of regions I converge to. So imagine running 1 million instantiations of stochastic gradient descent and then finding some notion of a probability distribution that it induces on the weight space after these 1 million runs. And I would like to understand the qualitative properties of this probability distribution. And this mathematically boils down to thinking of SGD as a Markov chain. It is a complicated Markov chain because the noise depends on the state, so on and so forth. And we were interested in understanding the distribution, steady-state distribution of such Markov chains. What we found is that the noise in SGD, the covariance of the mini-batch gradients, is extremely, extremely non-isotropic. So SGD as a Markov chain does not move in all directions with equal mobility. And once it goes in one direction, the probability of you coming back in the same direction would be equal if detailed balance were being followed. But because the noise is not isotropic, it is no longer the case. And you can get very exotic phenomena. So in this paper, I was analyzing things using something called as non-equilibrium thermodynamics, which is one area which always deals with these kinds of Markov chains where detailed balance is broken. And you can get all sorts of exotic behaviors. Let's say the trajectories of SGD don't have to converge. They can travel arbitrarily in some subspaces without ever changing the loss. The critical points on the loss function induced by such kind of trajectories don't have to be critical points of the loss function f that you're trying to fit. Really weird and unusual stuff like this. Okay, so second peculiarity is that the noise in SGD is very far from isotropic, and that causes the training dynamics to be really something unusual. It is not just a case of you finding a local minimum and then bouncing around at the critical point. It can look quite different. Okay, so in this talk, I will try to disentangle these two phenomena. I talked about this. We exploited these objectives to train neural networks, and some of these algorithms for training models are really quite efficient. So even after the first epoch, this is obtaining an error that is as good as SGD at the end of training. Roughly, it would be 2 to 4 times faster, depending on who implements it. Anyway, so in the rest of the talk, I will try to convince you that when we say that we want to understand deep learning, there's a huge elephant in the room. So there's many people who are interested in understanding deep learning today. I'm not the only one. And typically, you'll see that some people say, oh, neural networks are very good because they're over parameterized. Well, small neural networks also work well. You can try it on your laptop, it works just fine. And at a more conceptual level, an over parameterized model has a lot of null parameters that are not restricted by the data. So why the heck should they matter? Right. So I am allowed to ask these questions. There'll be some other people who say, oh, deep learning works because of implicit regularization that comes from your training process. Now, if you open up arXiv over the last many years, you'll find thousands of papers which have modified the training procedure. Some have changed the stochasticity, some have tweaked SGD in many, many different ways. All of these algorithms also do work. So if implicit regularization is the reason why training the network works, then all these methods are also doing different kinds of implicit, and they all also work. That is a little too much implicit for me personally. So it cannot be the only reason. Maybe it is one of the reasons. And I can go around and then talk about many different things or many different ways of understanding these things. Some people will talk about architectures. Well, if convolutions were the money a few years ago, they were the real reason why deep learning was working. Today, transformers also work. 5 years later, some other architecture will come up and that will also work. So it cannot be that simply the inductive bias of convolutions is the one that is necessary, or the inductive bias of self-attention is the one that is important. There is something else at work. I will try to convince you that the elephant in the room is simply the structure of the task or the structure of the data that we fit these models on. In machine learning, we should be, technically speaking, in the business of modeling data, but we never actually do it. If you take a statistical learning theory book, the first thing that it does is that it takes the data and then throws it out of the window and starts talking about the models that we fit on the data. And this is really why we get into a lot of circles and pitfalls in understanding why machine learning works well. So in the rest of the talk, I'll try to convince you that the data has something really nice, some really nice properties, and all the peculiarities that we see in deep learning are really just an artifact of the data, not so much what we do to it. So this is a paper that was presented at ICML a couple of months ago. Rubing Yang, who is a PhD student in my group, worked on this paper, and Jialin Mao helped her on it. I'll start with an experiment. So focus on the blue line. The blue line are the eigenvalues of X transpose. So X is a matrix where each column of X is one image. I take my images, in this case CIFAR10, which has 32 cross 32 images RGB. So that gives you 3072 different dimensions. And I string them up as a vector. So number of columns equals the number of images. Number of rows is 3072. Correlations of the pixels can be calculated as X transpose. And so what the blue line is telling you is that data lives in an effectively low dimensional space. By the time I finish about the first 100 eigenvalues or first 100 eigenvectors, I drop by about 4 orders of magnitude in terms of the magnitude of the eigenvalue. So it is really strong, this low dimensional structure of the data. And this shouldn't be a surprise. So there is many 50, 70 years of thinking like this that says that, especially in computer vision or neuroscience, where we believe that data comes from some low dimensional manifolds. And this is simply showing you the same thing. What is surprising is how low dimensional it is as compared to the embedding dimension of the input images. Okay. Another peculiar thing to notice is that after this initial drop, the eigenvalues are distributed uniformly in the rest of the tail. So data is not exactly low dimensional, at least not in this particular linear way of looking at the correlations. It has tiny signal in every part of the subspace, but really tiny signal. So 8 orders of magnitude or so lower than the head, the tail is. Okay. Now the blue line is just about the input images, nothing to do with the network yet. What we have shown is that when the blue line looks so, essentially every quantity that you can calculate inside the network also looks like this. So focus on the orange line now. The orange line are the eigenvalues of the Fisher information matrix. The Fisher matrix is, you can think of it as the curvature of the output space of the model. So the model predicts some outputs, 10 classes, for instance, and you're talking about some curvature of the output space. And the eigenvalues of the Fisher matrix are correspond to different ways in which the model makes predictions. Okay, so when you think of a small eigenvalue of the Fisher matrix, it corresponds to an eigenvector in which I can perturb the weights by huge values, by huge orders of magnitude, without changing the output of the model. So because it is about 7-8 orders of magnitude smaller than the head. This is the reason why we call such models sloppy. They are sloppy because there is a huge number of parameters being thrown at the data, and then these parameters are so weakly constrained that you can do whatever you want to them in these specific directions, not the bare parameters themselves, but these eigenvectors, without affecting what the model does. Okay. To help you understand a little better, it will you can think of linear regression. For linear regression, the Fisher matrix is identical to XX transpose. So the orange line and the blue line are identical for linear regression. And what I'm showing you also here in this plot is that for this large convolutional network trained for doing classification on CIFAR, they're also pretty damn close. Okay. The Hessian, yes.
Is it like after training or like
after training?
After training.
Yes. So before training, it looks slightly different from this. It is a little more flat, but it still drops at the head. Yeah. Any other questions? So the Hessian is the curvature of the loss, just like the Fisher is the curvature of the output. The Hessian also has a sharp drop in the stiff subspace of the data matrix, and then a similar decay. The Hessian is a lot more expensive to calculate, so we only calculated, I think, in this case, 1,000 eigenvalues. And essentially many other quantities. So correlations of activations, correlations of Jacobians of different logics, gradients of the loss with respect to different activations. All of these quantities have the same shape. They drop quickly and then they're distributed uniformly in terms of their eigenvalues. Now think about this, right? So I took this picture from Plato's theory of forms. And if you want to imagine what the head of the eigenspectrum looks like, it corresponds to pure caps. The most salient caps in the world lie in the head of the spectrum. Okay, the stuff that is very rare lies in the tail of the spectrum of the data. So blue sky lies in the tail because blue sky doesn't vary much across images. A blue dog also lies in the tail because there is very few blue dogs in the world. When you have such data, if the Fisher matrix is shaped like this, then you can happily overfit on the blue dog and call the dog a dog simply because it is blue, or actually call blue because it is a dog, without hurting yourself, because the modifications to your model are so small compared to the salient modifications to the model. Okay, and this is very important to appreciate. So noise can hurt you. Noise can come in the small eigens in this subspace, but you will not make incorrect predictions if you overfit, simply because noise is the eigenvalues corresponding to noise are so small. If noise were to come and hurt you in this subspace, you would make predictions, but then I wouldn't call it noise in that case. Okay, so for such kinds of tasks, for such kinds of input distributions, and nothing can overfit, not deep networks, not any other machine learning one. These are fundamentally easy tasks. Okay, so one way to think about this is neural networks work well, not so much because of anything specific about the networks themselves, but really because the data is so nice. I will show you in the next few slides that if the data is not like this, then they can overfit happily. Okay. So mathematically, we can show the following things. So I said that if the data is shaped like this, then if the data is sloppy, then the Fisher is also sloppy. We cannot prove this complete sentence crisply, but we can prove it most parts of it. And here is one version. So we can prove that the trace of the Fisher matrix or the trace of the Hessian are upper bounded by the trace of the data correlation matrix times some function of the weights. Now, this is a relatively easy thing to show. And one way to understand this is as follows. So let us say that I have a fixed data set, in which case the blue stuff is fixed. I can train many different kinds of neural networks on the same data set, and I can control the weights in any which way. Let us say that we control the weights to remain in a small L2 ball, so I can uniformly bound the right-hand side of this equation, of this inequality. The left-hand side is the sum of the eigenvalues of the Fisher matrix. So if the right-hand side is upper bounded, then the left-hand side at least has to decay. So I cannot show you that it decays exponentially, but this convinces you that it at least decays. If you think of an inner product kernel or an infinitely wide network, then you can also show that it decays exactly with the spectrum of the input matrix. Okay, but this is a general statement for any which architecture. Doesn't matter what the depth is, doesn't matter any other specific of the architecture. You can also prove, you can also kind of go down one level and prove the following thing. The Fisher matrix is a big matrix, number of weights times number of weights, and we can analyze different blocks of this matrix. So by looking at the correlations of the logics with respect to the weights corresponding to only that particular layer and setting the off diagonal blocks of the Fisher matrix to 0. We can show that the eigenvalues of this particular block of the Fisher block corresponding to one layer are dominated by the eigenvalues of the correlation of activations of that particular block. Again, this is not that difficult to show. It is actually a pretty basic analysis in linear algebra. The activations of that block and the weights of that block are intimately related. The Jacobian of the logics of the model with respect to the weights of this block, you can upper bound by the spectrum of the activations. Okay, but in this case, we can show that if the activations decay exponentially, the eigenvalues of the activation decay exponentially, then the eigenvalues of this particular block will also decay. And in experiments, we know that this quantity decays exponentially. Now, it would be nice to say that if the inputs decay exponentially, then the Fisher eigenvalues also decay exponentially. But that is, I think, not just something that we cannot do, but really very hard to do, because the weights can affect the spectrum in many, many different ways. Even if you just assume random weights, you're doing like this nasty random matrix calculations across multiple products. Okay, but moral of the story, we can prove that if the input is sloppy, then some stuff relating to the Fisher has to be sloppy. An experiment that certainly seems to be the case. Okay, so everything that I've said, I talked about neural networks, but it doesn't seem to be very specific to neural networks. So I'll give you one example. So in systems biology, people study what are called protein intracellular signaling networks. And for mathematicians, you can simply think of this as a system of ordinary differential equations, where the differential equations consist of what is the concentration of one particular protein, what is the rate constant of that chemical reaction, etc. And the stuff that they're controlling is the output, which is typically the enzyme that you're regulating or some other protein that catalyzes some other reaction, etc. Okay. I am allowed to calculate the Fisher information matrix of this system by thinking of the output and thinking of how sensitive the output is to variations of the input. The input could be the concentration of the proteins or the kinetic rate constants. The Fisher of these kinds of system is also sloppy. So these are the eigenvalues of the Fisher. This is a very beautiful paper that you can read about it. So this is a totally different problem. Nothing to do with images and neural networks. It is not even a model per se. It is just a statement about the data. And this is the Fisher matrix that is sloppy. You can take many, many other problems. So this one is an Ising model. Ising model is a very, very old and classical way to think of a pretty abstract way to think about magnets, to be honest. But there are spins that are likely to take similar values to their neighbors depending on what the coupling between two spins is. And the probability distribution of an Ising model is the likelihood of all the spins taking certain values. I'm allowed to take calculate the Fisher information matrix of the probability distribution of an Ising model with respect to the coupling constants. How likely you want your, or how strongly you want your neighbors to take the same values as you. The Fisher matrix of this model, which has nothing to do with reality, is also sloppy. This is another one, which is a circadian rhythm model that is also sloppy. And these are many, many other problems across physics, chemistry, and biology. You can find more. All of them seem to share this trait that the output is a a very low dimensional function of the parameters of the model. So sloppiness seems to be a prevalent theme across many different parts of many different sciences. Here is one application of these results. Okay, most of you might know back-based bounds, but here is how one can introduce them simply. Think of a distribution Q. Q is a probability distribution on the space of hypotheses. So think of a distribution on the weight space, that is Q. Little e of Q is the test error of one model being drawn from this distribution Q. So little e of Q is the probability that I draw a hypothesis from a distribution Q, I draw a datum from my test data set, and I make a mistake on this test datum using this hypothesis, and this is the average over all such draws of models and data points. E hat of Q is the same thing for the training data set, where I draw a hypothesis from Q and I evaluate its test error. So both of these things are probabilities of you making a mistake on the test data point, and this is the probability of you making a mistake on the training data point. People in learning theory like to write down inequalities of the following kind. The test error is less than equal to the training error plus some complexity term, which decays as 1 over square root of the number of samples I have for training. And the numerator is some notion of how many hypotheses I put non-zero probability mass on. So ignore P and stuff, that is simply a prior. But the KL of Q comma P is the total number of models that Q puts its probability mass on. If I choose a very large hypothesis class and don't give you too many samples to discriminate between this hypothesis class, then this complexity term will be very large, and I should not expect a small generalization. Okay. Now, this is being done for last 30 years. So there are many ways of doing this. Fact-based bounds are just one particular way. And what people have been very upset at these days is that when you plug in numbers into these inequalities, you really get very unsatisfactory answers. So for deep learning, this quantity is essentially zero. We always get very good error on the training data set. So let's just set it to zero. The test error of neural networks is also very nice. So let's say that is 5%. So there's a 0.05 probability that you make a mistake. The right hand and the complexity term for neural networks is enormous. It's roughly like 100, 1000, etc. So these inequalities are rendered completely vacuous by neural networks, because at the end of the day, they are saying that the probability of you making a mistake on a test datum is less than 100. Now, I don't need a theorem to convince me of this. Okay, and so this has been a huge disconcerting thing for learning theory, because you built a theory about 30 years ago and somehow no one bothered to plug in numbers into this theory all this while. And so now we are upset at the fact that the theory doesn't quite work. What we can show, and so there has been a lot of debate about whether learning theory is good enough to understand neural networks or not. People are trying to build different kinds of learning theory, etc. What we can show is simply by taking a quadratic approximation of the KL term. So you take a critical point, you calculate, you take the Hessian at the critical point, and you can optimize this entire right-hand side analytically over a Gaussian distribution Q around center at this critical point, and you will get you'll calculate the covariance matrix of this Gaussian. With just this half a page of calculation, we can obtain an analytical non-vacuous bound on the generalization error of neural networks. And it is also pretty nice. So for instance, for a 3-layer network on MNIST, the right-hand side of this equation is 0.38. Doesn't mean it is tight, but it does suggest that we don't really need new theory to understand generalization in deep learning. The existing theory is just fine. We just need to apply it correctly. If the Hessian is sloppy, then the bound is nice. Okay, and this is just an analytical bound. We have also done a lot of complicated numerical bounds using this, and we can get very tight results. So for instance, for things like convolutional networks, we can basically get tight generalization bounds by optimizing the right-hand side numerically. But even analytically, you will get non-vacuous bounds. Now, the utility of a generalization bound at the end of the day is to simply convince the theorists that they are not entirely wrong. But one way to think about this calculations is that learning theory fundamentally does not care. So you don't see anything here about the properties of the data set. And that is the real key missing piece in these kinds of inequalities. Once you incorporate properties of the data set, which in our calculation, we simply incorporated using the eigenvalue of the Hessian, but presumably in the future, we would want more explicit notions of how the data controls this capacity term, then we will have a reasonable theory of understanding generalization. Here is one very cute thing to remember from these calculations. So we know that neural networks are very large objects, millions and weights, even billions these days. These calculations of the pack-based bound suggest that the effective degrees of freedom inside the trained networks, that really the number of weights that are constrained by the data is actually something that is very small. So roughly speaking, you can take the eigenspectrum and look at the elbow of the eigenspectrum, and the number of eigenvalues to the left of the elbow is really the effective degrees of freedom. And an intuitive way of understanding this is that the pack-based bound really tries to optimize the training error and the complexity term. If you change the model, if you change the distribution Q in the stiff subspace of the Fisher, then you get a large hit to the training error. If you change the Q in the sloppy subspace of the Fisher, then you can actually fit the complexity term very well. So the elbow is really the balance that a good pack-based bound or a tight pack-based bound strikes between optimizing the training error and optimizing the complexity term. And mathematically, we can define something like this. So the number of eigenvalues that are larger than some threshold is not really important, it's the scale of the prior divided by the number of samples. This is the number of degrees of freedom in a trained model. And what is very nice about this inequality or about this definition is that as the number of samples goes to infinity, the network gets to use its full capacity. So it is not as if the network has a small capacity to begin with. It is just that the effective capacity of the model is modulated by two things: the eigenspectrum of the data, the simplicity of the task, but also the number of samples that I'm giving you to fit the task. And this is pretty nice. So there is some kind of automatic capacity control that is happening because of the number of samples and the structure of the data. You can calculate this quantity, the effective degrees of freedom, and typically it is very small. So for most models that you will use or you will train, for most difficult problems that you will train for, it is less than 0.5% of the number of weights. So you have a model with 1 million weights. You are fitting a function with about 5,000 degrees of freedom. It should not be a surprise anymore why you can get good generalization with 50,000 images or 100,000 images. Okay. It is not as if you would do well by just fitting this small model, but the large model after you fit it effectively is this small. Okay. So here is another experiment. So we talked about how generalization occurs when the task is easy or the task is low dimensional, to be precise. Does it still occur if the task is not low dimensional? So on the x-axis is what we call the sloppy factor. The sloppy factor is the slope of the eigenspectrum after the elbow. So if the slope is very close to 0, that means it is flat. And that is really where you see the curse of dimensionality hit you. If the slope is very large, then you have a simpler data set, effectively a more and more low dimensional data set. So what we did is we sampled synthetic data from a Gaussian with different covariance matrices on the x-axis with different slopes. And we created a random feature network with 2 layers. So this is a fixed neural network with randomly chosen weights that labels this data. This is a very classical thing to do in physics. You think of the teacher-student model where the teacher creates the data and the student tries to learn the data created by the teacher. And so this is a teacher with 100 hidden neurons, and it is fit by a student with 10 hidden neurons. This is a teacher with 20 hidden neurons, and student is a 500 hidden neuron network. Okay? And there are how many? 1, 2, 3, 4 times 5. So 20 different experiments, one each point on this plot. And every one of these points has a 0 training error. So the student is fitting the data created by the teacher perfectly in every single case. But what you will notice is that if the eigenspectrum is flat, then the student does not get to generalize. And this shouldn't be a surprise. The eigenspectrum is flat, so you need a lot more samples to generalize for the student. And all these experiments have the same number of samples. If the eigenspectrum is sloppy, then you can overfit and without hurting yourself in terms of generalization. So this is kind of a counter example which says that if the data is not sloppy, then you need lots of examples to fit it. Even if the data was created from a nice task, in the sense that there is an existing model that you should be able to fit the data that you should be able to discover. Right? It is not arbitrarily labeled data. Yeah. So neural networks can overfit if data is not sloppy. And some of you might know these papers called benign overfitting for linear regression. This is simply the same phenomenon for nonlinear models. Okay, so here is my mental picture of how learning occurs. Some of it we have proven, some of it we are in the process of showing. Think of the manifold of models that you're trying to fit. You initialize on this manifold somewhere, your random neural network, and fitting a model at the end of the day corresponds to you going to some other point on this manifold. That is the true model, the nature's model that you're trying to fit. The modifications to your neural network typically happen in the stiff subspace of the Fisher matrix, the subspace corresponding to the large eigenvalues. They are the ones that are modified the most. And we have also shown this. There is very small amounts of modification that the network undergoes in the sloppy subspace. And so at the end of the day, when you fit a model, you find something that looks like the corner of a manifold. So this is some upcoming work that you might see soon. And what we believe is that typical tasks all lie very close to each other at the end of training. So this is not something that we talked about in this lecture, in this talk so far. But the moral of the story is that the manifold of models that you are learning is quite low dimensional. And that is why optimization seems easy, because it is fundamentally tracking this low dimensional manifold. Okay? Now, when you think of the two peculiarities that we talked at the beginning of the talk, the fact that the Hessian has a lot of zero eigenvalues is simply the same thing, is simply that the sloppy eigenvalues, I never bothered to calculate it. That was many years ago. I only focused on the zero eigenvalues. But really, the Fisher and the Hessian are sloppy. It is not that they're low rank. The noise of SGD being non-isotropic, well, the noise of SGD is actually very close to the Fisher information matrix. So the noise being non-isotropic is again simply an artifact of the Fisher being sloppy, which is an artifact of the data being sloppy. Okay. Any questions so far? Okay. I want to tell you another very cool thing that happens if you think about data as a first-class citizen in machine learning. And here is one way to do it. So let us say that I give you a biased coin, and I want you to estimate the bias of this coin. If you want to do Bayesian inference, you will say, okay, I will put a uniform prior on 0 to 1, and then I start tossing the coin. And I toss the coin many, many times until my posterior converges to some point, and I will give you that answer as the bias. Now, you need a lot of coin tosses because you chose to put the prior on an infinite number of models or infinite number of different possible biases. Okay, this is just a fact. If I were to only allow you one coin toss, what prior would you pick? So you can think about it yourself. You have one bit of information that is coming to you from one coin toss. This coin will come out either heads or either tails. With this one bit of information, you can only distinguish two models. You cannot distinguish an infinite number of models. So in this case, you should be putting half probability on 0 and half probability on 1, because the coin only comes out either heads or tails. If you put some probability on 0.25, then you would not be able to say whether this is the correct model for my data or not. Okay. Now this is a very weird experiment because no one has thought, or you haven't thought what happens when data is a finite quantity and you're doing Bayesian inference with such finite samples. But many would argue that Bayesian inference only makes sense when the data is finite. If the data is infinite, then there is nothing to do inference. You just take the empirical average and things work fine. Okay. Mathematically, this is something called as a reference prior. And this prior is a prior that maximizes the mutual information between the weights and the data. And if you write down the mutual information, you will see that it is the average of the KL divergence between the posterior after you look at the data and the prior before you look at the data. So when you average, when you maximize the KL divergence of the posterior and the prior like this, you are letting data drive the posterior, not the prior. This is a very different way of looking at regularization or inference than what you're used to classically. Classically, we say that there could be noise in my data, and I don't want to be affected by that noise, so I use a prior to protect myself from the noise. This is the exact opposite. I give you very small samples to do inference with. You better believe that the samples are good, because 6 mice died to give you those samples, and that is all the data you have, so might as well trust it. I use a prior that allows me to find the right set of models from this small amounts of data. Okay, I don't want my posterior to be dominated by what prior I choose. I want it to be dominated by the data. Okay. So mathematically, this boils down to you optimizing or maximizing the visual information between the weights and the data. If I give you many samples, then the prior that you put will have many more atoms. And in general, for any finite number of samples, the prior is always putting mass on a finite set of atoms. Okay. As the number of samples goes to infinity, this reference prior converges to Jeffreys prior for one-dimensional distributions. So everything is nice. The Jeffreys prior is a flat prior in the space of models. So you're putting equal amount of prior on every model in your hypothesis class. Now, the cute thing is that these things were discovered by Bayesians or formalized by Bayesians in the late 70s, when they got very upset that subjective priors are just subjective. We would like something that is more objective. And this is the kind of objective priors that people have. There are many others. This is one more common one. The cool thing about this for us is that neural networks are a very large hypothesis class. It's not very easy to say, I will fit a small network if your data is complicated. But the reference prior allows you to select a smaller hypothesis class from your complicated hypothesis class if it knows that you will get few samples to train with. Okay, so you're not choosing simpler models, you're choosing few complex models, and this is a very different way of doing inference. So this is some very nice mathematical work that has very deep connections to things like predictive coding, information bottleneck, or predictive information bottleneck. We presented it at ACML this year. This is called deep reference priors. This is the first time anyone has ever dared to implement a reference prior. After 40 years of writing it down, you will see it as homework problems in some statistics classes. No one ever tried to calculate it. This is the first time. So Yansong Gao and Rahul Ramesh worked on this. Yansong is looking for jobs. So if you have some, let me know. He has some very beautiful work on understanding the space of learning tasks, which I did not talk about here. That is usually the other talk that I give. But here is one way to think about this. So when you want to optimize this prior, what you do is you set up one neural network corresponding to one atom, and now you're trying to maximize the mutual information to find the right prior. The average over the distribution of data, it can be done using unlabeled data, so unlabeled images, and then you replace this expectation by the empirical average. Here is how it looks in a picture. So we have developed some tools to study the function space of networks. So, but let us not worry about how this picture was created. The prior looks a little bit like these green points. Each point is very different from each other in how it makes predictions. Some models say that this is a cat with 100% probability. Some others say that the same image is a dog with 100% probability. Together, they are very diverse, but all of them are confident and could be wrong. Okay, when I show you a test datum or a datum for inference, one of these particles strikes gold. The coin either comes out heads or a coin comes out tails. So one of those atoms strikes gold, and that is how you do inference with small amounts of data. You carve out a small hypothesis class from your large hypothesis class and let data pick one of these points. Okay. So here is the picture again. This is the hypothesis class that we are dealing with. The reference prior selects diverse models from this hypothesis class in the hope that once you see the data points, one of these will be your true models. If you have many more data, then it will also put probability mass on the interior of the manifold. And we can calculate, you can show some of these things using calculators. Okay. One very cool application of this is to formalize semi or self-supervised learning. And if you write down the reference prior, it is quite easy to understand for classification. There are all these atoms W that correspond to the prior. Each of these atoms is minimizing the entropy of its predictions on unlabeled data points. So I give you an unlabeled datum for model 1, it says, oh, this is a cat. The other one takes the same datum and says that, no, this is a dog with a very high probability. So all of them are confident, they're minimizing the entropy. The average or the ensemble average of all their predictions has a very large entropy. So together they're making very diverse predictions, although each of them is very confident and could be wrong. Okay, so this is how you fit diverse models. And mathematically, this is an objective. You can implement it in many, many different ways. And what we have noticed is that a lot of little tricks that people do for semi-supervised learning or self-supervised learning can be derived from this one objective. Roughly speaking, the union of tricks in semi-supervised learning is actually this objective. So in some sense, it is a theory for how to learn optimally with any given data. And it is optimal in the sense that you're maximizing this much information. You can also implement it as an algorithm. And so you get pretty nice results. You basically match the accuracy of the best methods for semi-supervised learning, which are spectacularly good to begin with. So with roughly 5 labeled samples per class for CIFAR 10, you get 85% accuracy, which is basically making the argument that this is not just a theory for semi-supervised learning, it is also a reasonably faithful theory. It matches in terms of its numbers. There are nice connections to predictive coding that we are trying to explore, but it's a very powerful way of doing inference with high dimensional models, even when you have small sample sizes. Okay. How much time do I have? Okay. Yeah. So here is another application. So I talked about using unlabeled data to calculate the reference prior. This is some way of selecting the right set of models. You can also think of a slightly different problem that says, I have a source task. I want to get good performance on my target task. How should I train on the source task to improve my performance on the target task? This is something called as transfer learning. And what you will see today is that people fit a model on the source task and then fine tune it on the target task. Now, obviously, if you completely fit the source task, then that cannot be a good answer for the target task, because you're discarding all the information from the source task, and everything that you deem not relevant to the source task is exactly what is relevant to the target task. And we have some papers which formalize this, because if you throw away nuisances from the source, what is nuisance for task 1 is actually information for the second task, right? If it were not the case, then the 2 tasks would be the same things. So clearly you should not be overfitting on the source if your ultimate objective is to fit the target. But how much do you underfit on the source? Well, the answer is, again, the reference prior. The reference prior tells you how to optimally make use of the source data when your goal is to use the target data. You create a bunch of models that are as diverse on the source data as possible, while still maintaining the fact that you want to do well on the target. Okay. So we can kind of formally write down what counts as optimal transfer learning or optimal pre-training for transfer learning. Okay. And here is how it looks. So this is a small experiment where we took different classes of CIFAR 100. Vehicles 1 is a set of 5 classes, vehicles 2 is a set of 5 classes. And so the columns are source tasks on which we pre-train using the reference prior. And the rows are the target task on which we fine tune, roughly speaking. In this case, it is actually Bayesian inference instead of fine tuning on the target task. And so all these numbers are accuracies that you get on the target. If I train on vehicles 2 And when desire to get good performance on aquatic mammals, I get 47% accuracy on aquatic mammals. If I want good performance on vehicles one, then I do much better. It is 70%. Okay. Fine tuning, it is actually good fine tuning, will give you much worse answers than this. So this is actually trying to make the case that if you want to do well on a target, overfitting the source is obviously the wrong thing to do. You need to think about pre-training a lot differently if your eventual objective is to actually to do transfer learning. And these are pretty drastic differences in the numbers. Typically, people will have large number of images for the source and the target, and the tasks that they care about are also much closer to each other. And so the differences will be slightly smaller. But this is the correct way of doing things. Now, we might not want to do this because it is more complicated in a lot of real applications of transfer learning, but we can hack this objective and come up with more reasonable or more implementable versions of these objectives. Yeah. So to conclude, I want to make two main points. One is we know deep networks are very weird things, but I would contend that they are peculiar, not because of different architectures or different training regimen or different regularization. They're peculiar because we just chose to ignore how the data plays a role in the functions we fed. If we think deeper about the kinds of the structure in the data, then a lot of this stuff that looks peculiar goes away. And the second one is a little bit more philosophical. So I find it very surprising why data has structure to begin with. And there are many ways of understanding this. So if you're inspired by statistical physics like I am, there is a lot of molecules in this room. And then we gave this bunch of molecules a name called a chair, or this other bunch of molecules name called a dog, because next time we see the same thing, we want to identify them easily. Right? So there is macroscopic structure created by nature. And then there is semantic structure on this macroscopic stuff that is created by humans. And in some sense, there's a long tradition in physics of studying how the macroscopic structure emerges. What is less done is to understand why we give names to objects. We give names to chairs and cats and dogs. We don't give names to leaves or stones because we don't care to identify them. And because the way to identify them does not rely on salient features. It requires lots of complicated features, and stuff that we give names to usually has a lot of salient structure. So in some sense, the tasks that we deem useful or we create are actually learnable, or in some sense easily learnable. The stuff that we do not care to do, let's say distinguishing between Mozart playing on a Wednesday versus Mozart playing on a Monday, there could be some distinguishing signal, but this is not an easy task to do versus Mozart playing on a Wednesday versus me playing on any day. It's a very straightforward thing to distinguish, right? So we do stuff that is learnable and then we basically ignore the rest. And those are not useful tasks. In some sense, we shouldn't be surprised that the tasks that we created are easily learnable at artificial learning. And to conclude, so there's a lot of debate about not understanding deep learning, and understanding has different meanings for everyone. I'm not saying this is a complete picture of understanding neural networks, but it does suggest that what we think are highly intermingled concepts like architecture, choice, and optimization and generalization could actually be resolved by simply putting data in the centerfold and the rest of them as offshoots of the properties of data. So I'll stop here and take questions.
Okay, thank you for the nice talk. Are there any questions from the audience? Also on Zoom, you can feel free to type a question into the chat box or into the Q&A box.
So in your experiments for deep networks, was there any effect of initialization? Because if you have like a high initialization, it is in the NTK regime, I don't know about it, and then if a small initialization, it is in another regime. So in your experience, you observe those things?
Yes. So for normal initializations, unless you're being pathological, the initialization doesn't matter. What we have found is that the functions that you learn across different initializations, across different training regimen, etc., are all very, very similar to each other. If you initialize in bad ways, let's say you increase the variance of your weights by a lot and then shoot off in some wrong direction by training on a bad task or randomly scrambled labels, then you can get poor generalization from these models. That is not difficult to see. But what seems to be true, so what is obviously true is that neural networks are units of approximators. Nothing that I said contradicts with that statement. You can fit any task in. What I did say, what we have found is that what you typically learn on data sets is always nice and low dimensional. You can easily learn stuff that is not like this.
Yeah. And also, since you are trying to say that an important role is played by the input data and the architecture optimization and the other things are not that important, or
I don't know how to quantify the not that important part, but they certainly seem to play a weaker role.
But how come other models like boosting or like other ways of doing ML are not working well compared to deep networks? How come that's happening?
So I would personally contest that a little bit. So things like boosting actually work extremely well. So you can try this experiment yourself to give you one evidence. We have some papers on using on building predictive models for things like Alzheimer's disease using very complicated data. So MRI images like genomic features, clinical stuff, etc. And for these models, boosting actually works spectacularly well, way better than anything that you would do with a neural network. Doesn't mean boosting is better than neural network. Both are units of approximators, but simply that we don't know how to use the MRI images as well as what you would do with the structural features. So there are incidents, there are cases where boosting does work. Now, obviously, convolutions are nice if you're using images. So it is not that boosting is as good as neural networks on images, but certainly for tabular data, boosting is great. You will see that the kind of functions fitted by boosting, even for image data, actually are pretty similar to the ones fitted by neural networks. This is some upcoming work, but yeah, it is very, there is not that many things you can fit on the data and yet predict well. It's a little bit like saying, I have data that comes from a quadratic polynomial. You can choose whatever polynomial you want to fit to this, but if you are forced to predict well on the quadratic polynomial, there is not that many different things you will fit, at least within a restricted part of the domain. Boosting is gradient descent.
Gradient descent or like alternative methodization?
Gradient descent in the function space, so executes.
Yeah, but the architecture is different, right? Because you
You
only have
yes, yeah.
basically.
So I mean, think of the space of functions being this room. I would like to do gradient descent in this space. Now, the architecture determines which directions I'm allowed to move in and which directions I'm not allowed to move. For units of approximating architectures, I'm allowed to move in many, many directions. But this is the entire space of functions I want to move it, right? There is one trajectory that I want to track. My network has a manifold that does not allow me to track this trajectory. A bigger network has a manifold that allows me to track most trajectories. But since these are all big models, I should be expected to track many trajectories.
Okay, how about other models like K nearest neighbors? Is that also good?
We can calculate this. We can do some kinds of analysis using non-parametric models also. So just like I defined the number of degrees of freedom inside the network, we have also defined the number of degrees of freedom for a K-nearest neighbor model. Yes. And you can run a fact-based bound for it just fine. It is also surprisingly nice. So the non-parametric model, I mean, it is a silly thing to say that the non-parametric model has a notion of capacity, but it's an operational notion of capacity in the sense that how much does the generalization decrease when I add a few more data points.
I have a question too. So I think your message on the pack-based bounds is sort of that they look vacuous at first, but then because the model has fewer degrees of freedom because of the data, essentially, they actually become non-vacuous in some sense. So do you have an answer though to why? I mean, so from my understanding, if you use a neural network that had actually, that few degrees of freedom, you wouldn't be able to train it well on a modern task like CFAR or ImageNet or something. Do you have some explanation for why you have to be in this over-parameterized regime when your model is only going to learn a small number of degrees of freedom?
Yeah, so I don't have a concrete answer yet, but I have hunches. What I believe is, so think of a quadratic loss where the data is like this. It will have a very bad condition number because there is huge eigenvalues and there is very small eigenvalues. You will spend a lot of time making progress if the signal is correlated with some of the small eigenvalues, some of the labels. You have two choices. You can pump in a lot of epochs and exponentially many epochs, in fact, in the dimensionality to fit all these eigenvalues. Or you can initialize yourself a little bit better in this subspace and fit them quicker. What over-parameterization seems to give you is the second one, where you are closer to the eventual point you want to be due to initialization. But the small models, if you just keep training them, they will fit it if they need to have that signal. Right? So we have seen such things in experiments. I don't have enough evidence yet to just say concretely that this is what happens, but this seems likely.
So it might just be that it takes longer to train the smaller models.
Yeah, that much we know. And people don't bother to train that much. It's actually exponentially many epochs, so you would never be able to do it anyway.
Okay.
So I'm sure that no networks exploit their simplicity in the data.
Yes.
So on the other hand, actually, it's kind of a disadvantage because they try to oversimplify that. And if they're not so simple, so
Yeah. So what I have noticed is that adversarial attacks will take this entire tail of the eigenspectrum and lift it up. And that shouldn't be a surprise. It basically says that for fitting adversarial samples robustly, I need lots of more sample size. I need, so the effective dimensionality is not this small. Now, when we face adversarial attacks, there is also another handicap that the network has, right? Because it is trained on data that looks like this, and it is being shown images that are a little bit outside the manifold. So what these results that I have are only about understanding what happens in the standard case when data comes from this manifold. I don't know, for instance, the error, how it decays when data comes from slightly different subspaces. But what definitely seems true is that if my adversary is allowed some limits on the power that it is supposed to use, if it perturbs in the sloppy subspace, then it cannot do much harm. It has to perturb somewhere here in the stiff subspace, in which case it cannot perturb much. So in the adversarial learning world, people always just talk about the norm of perturbation. I think what is more interesting to study is the directions in which the perturbations occur. Perturbations here are perfectly fine because they won't change the model much. Perturbations here are the ones that you are trying to fight. But then the adversary will have to be also very powerful, and in which case I wouldn't call it perturbations, I would call it an enemy.
You go back to the figure you have with all the different information for the different tasks. I just want to make sure I understood it. So
Which one?
a couple slides back. Yeah, this one. So when I'm looking at all the different colored bars, am I looking at this as like percentiles, like?
No,
number
no,
of
no, these are
eigenvalues?
the eigenvalues.
So those are the eigenvalues. Okay.
Yeah, so I like to just plot the eigenvalues themselves. There are many papers which have plotted the distribution of eigenvalues, and they did not notice this because the distribution eigenvalue just collapses all the sloppy subspace in a tiny part of the histogram. So people have always been talking about low rank Hessians and low rank models, etc. But the cool stuff happens actually in the sloppy subspace, not just the stiff subspace.
Okay, any other questions in the audience or on Zoom? Okay, so we will be having a follow-up session for graduate students, and if any postdocs want to join as well, just in 405 over here right after the talk. So please feel free to join us and ask more questions of Pratik. And so let's thank him again for a very nice talk.
I thought maybe he had